Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from 5.7. And these problems of 5.7 have to do with variation problems. And variation problems have a very specific formula to use to help us out with this. We've got variables that vary directly and variables that vary indirectly. And then there's a joint variation and combination variation. But let's specifically start off with direct variation. So I want to bring you down to this definition, and basically it says that, if I zoom in a little bit here, it says if x and y represent two quantities, then y varies directly. So when you see that language, real important, let's make sure this isn't too large. Yes, that should work. It says when y varies directly with x. Or you see the words y is directly proportional to x. So those two sort of catchphrases, I'll put little parentheses around that. You see that language, or if you see this language, if there's a non-zero number k such that we will have this equation to work with. And if you notice, that is very similar to our y equals mx plus b. Now notice that these equations, these direct variation problems, you can see that the b value is actually just going to be plus 0, so that's why we don't even show it. And your slope is your k value, and k is called the constant of proportionality or the constant of variation. Okay, that's kind of the k is the value that sets the variation, sets the tone of it, just like your slope sets how that line grows consistently. Okay. Another thing to take a look at is kind of saying the same thing in other words. If y is directly proportional to x, so there's that sort of catchphrase. If y is directly proportional to x, then y and x are related through the linear equation whose y-intercept is 0, 0. That's what I said. It's always going to be 0, 0 right there. And whose slope is k. And that's like what we were talking about. K, the constant of proportionality, is your slope. In previous, formulas, we used m for slope. Okay? All right, this also, the k value is going to be greater than 0, and x is going to be greater than or equal to 0. So we're always going to be looking at this first quadrant when we do this. All right, let's do some of these problems. I think we're ready to go. So when we take a look at this, it says the statement, and so I'm seeing that phrase, the statement t varies directly with s. There it is. T varies directly with s. When I see that statement, I automatically think t equals k times, and they're using the variable s. Also, I think, if we're plotting points on the graph, s is a lot like my x value, and t is a lot like my y value, so that's the order of it. They just asked us to identify the equation, and of course t equals k times s is going to be the third option right there. Okay, let's do a problem. Suppose that y varies directly as x. Once again, there's that catchphrase that allows us to really hone in on the idea that this is a direct variation problem. Once I see that, I know that y equals k times x is the equation I'm going to use. Now they're also telling us that when x equals 2, y will equal 10. So basically that's just the point, 2, 10. Now this is our x and this is our y. What we want to do on the first problem is find our constant of proportionality. Whoops. What we want to do is find our constant of proportionality, k, and we do have a k right there. All we need to do is substitute in, let's see if I can do this without making a big mess. Let's use some color. Let's go ahead and substitute in, our 10 is our y value, right? So it has to go there. So it's going to go there. And our x is our x value, which better go right there. And we have taken care of our variables. So 10 goes there. We still have a variable k, but that's what we're trying to figure out, what k is. So of course, all we have to do is divide both sides by 2, and we get k equals 5. So our k value is k equals 5, constant of proportionality. Now they say, please write the linear function relating the two variables in this form. Well, you know what your k value is, right? K value is 5, so now we know what the equation is. It's a real bad 5. There we go. So y equals 5 times x. Replace k with 5. Now we actually have the equation of this situation, right? What's the equation? Y equals 5x. And so they're saying, well, question. If I have an x that's 6, what's the y going to be? Well, easy, just sub it in, right? So we're just going to take our y equals 5 times whatever the x is, and they said the x is 6. So 5 times 6 is 30, so therefore y would equal 30. And we're done. That's a direct variation problem. Once again, direct variation problems always use the format of y equals k times x. And how do you know it's direct variation? It'll say y varies directly, or it'll say y is directly proportional. Do another problem. Let's see. Try to identify what it is from the beginning. Suppose that y is directly proportional. There we go, using the slightly different language, but you can hear of the direct part. So once we see that language, we know we better be thinking y equals k times x. Now they're going to give us some information. When x equals 3, then y equals 2. When x equals 3, y equals 2. Once again, that's x and that's y. Well, then we could say, let's see, y is 2, so put y there. And x is 3, so put x there. Right? Maybe I should have wrote that down there. So you can see the substitution, right? So y is 2, so sub in 2 for y. We're looking for k. X is 3, so sub in 3 for y. That's 3 for x, rather. Divide both sides by 3 so we can isolate the k. And we get k equals 2/3. The constant of proportionality is, and you have to be careful because they kind of switch it around with MyLab. It says type an integer or a fraction, so you want to keep this as a fraction. There's one where it actually says, please type it as an integer or a decimal, not a fraction. So just be aware. It says in parentheses how they want the input to be. The linear function is, well, now that we know the k value, let's do that. Now that we know the k value is 2/3, well, that just replaces the k. And so then we actually have the function y equals the k value 2/3 times x. And there's your equation. That is the equation or the rule that satisfies this given situation they defined. And now they're saying, oh, guess what? X equals 15. Can you tell me what y is? Yeah, no problem. Because I got this nice equation that'll tell me. It tells me y equals 2/3 times whatever x is. And however you want to do this, you could think of it as a fraction, right? So 2 times 15 is 30, and 30 divided by 3 is 10. It could also reduce first and then multiply. Anyways, it doesn't matter any way that you do it. If you do it right, you're going to get y equals 10. Okay, and now we're going to do a problem that is more of a word problem. It has kind of a situation background problem going on here. So we need to go in and first identify what kind of problem it is. It says the cost of gas C varies directly with the number of gallons pumped G. I can't see past my fingers, so I'm going slow. Okay, so right there, you better be thinking, I see direct variation. C varies directly. So C varies directly as G, and it's a good idea to try to, maybe I should put this stuff down here because of space. Let's see. But it's a good idea to realize that what do my variables look like here? Well, remember G is kind of like the X and C. So G, they told us G was the gallons pumped. supposed to be an A. Gallons pumped. And C is the cost of the gallons pumped. So let's see, what's it saying? It says suppose that the cost of pumping 9 gallons, okay, 9 gallons of gas is $38.70. So find the function that relates to this, the cost of gas. Let's see, find the function that relates the cost of gas C to the number of gallons pumped. So, we go through and kind of do the same thing we did before. Let's see, cost, I'll use green. And that just replaces that guy. And number of gallons pumped, which is G, happens to be 9. And that replaces that guy. And that'll allow me to get my C. And once I have my C, I've got my function. Let's do the work over here since I've got everything here. So I think I'm going to move this up a little bit just to give me a little space to operate here. So we found out that C is $38.70 equals K times G, the number of gallons pumped, which is 9. So if we want to solve this, we just divide by 9 on both sides. And we get K equals 38.7. 38.7 divided by 9 is 4.3. See if I wrote that down somewhere. Yeah, it's 4.3. Okay, and once again, with that, we now know the function for this situation by replacing that K with 4.3. So now we have, and if we could write this in function notation, notice it's written in function notation right here. It says C of G equals the K 4.3 times G, the number of gallons pumped. Basically, this is costing us $4.30 per gallon pumped. Seems a bit high, doesn't it? In that situation, I don't know the time period that numbers were calculated. Let's see. Use integers or decimals. Yeah, this one, see, it changed it up on us a little bit. It's saying to please use integers or decimals for the expression. So they want the decimal version of that instead of the fraction. Suppose that 5.3 gallons are pumped. Now let's see, 5.3, they're the gallons, and we said gallons were kind of representing in blue. So I'll go ahead and do that, 5.3 gallons pumped. What would that cost? Oh, okay. Well, we have the equation, so that's not going to be a problem. We want to know what happens when G equals 5.3. So, of course, that goes in for G right there. And let's go ahead and just do the new equation. It's going to be C equals K, which was 4.3 times 5.3. And so C, and I guess if I put it in function notation, C of 5.3, the input equals, and then multiply those two. And when I multiply the two, I get 22.79. So if you pump 5.3 gallons, it's going to cost you $22.79. Now it says to graph this, and I could estimate that, but it's pretty hard to get. Look at the numbers that we're trying to graph. 22.79. Ugh. So I figured, we must just round. And when I did that in my math lab, it said I was wrong. So I got to feel your pain, right? So it said it wanted to be exact, yet the numbers that we have, I want you to think about something. We've got a couple numbers we can use to graph this, actually. We've got 0, 0, right? We know it's going through 0, 0. We also have, we have this, right? Isn't that a number? That was 5.3 gallons pumped, and it cost me $22.79. We had another one from the beginning, I think, right? They told us way back at the beginning that 9 gallons cost $38.70. And so this is a nice whole numbers, right? 0, 0. But these guys, I don't have a 5.3. I definitely don't have a 22.79 that I could see. 22.7, 22, 21, 22.79 is like right there. But it's not exact, right? Because I don't have those marks on my graph. And when I went on the computer, it didn't have it. So that was kind of frustrating. That's a little bit frustrating. I figured they'd let us round, but they didn't. So then I thought, okay, now I know what you're doing. So no rounding. So this, like I said, it's a little bit of a pain. We've got to graph this graph right here. C equals 4.3 G, right? That's the graph we're trying to graph. We do know that the y-intercept is 0, so we can plot that point. That's the one we should use. But what number can we put in to get a nice whole number? And something that I was thinking about that would be easy is, if you had like 5.2 and you multiply it by 10, what does that do to that number? Whenever you multiply by 10, it just moves the decimal to the right one. So that'd be 52, right? If you had 1.3 and you multiplied by 10, that's just 13. So I started thinking, okay, well, if they want whole numbers, how could I get a whole number quickly? Well, I can get a whole number really quickly by just say, okay, I'm going to put in, what color did I use for G? I used gallons pumped, I used blue, I guess. So I'm going to put in a 10, right? So that's going to be, so now I'm trying to find another point. So now I got 10 for gallons pumped. And so what's that going to cost me? Well, that's 4.3 times 10 is 43. And now I've got some nice whole numbers. And I tried that on MyMathLab, and bingo, it worked and said I was cool and everything. So that's you kind of have to be tricky with it to make it work. A little bit annoying, right? So, and it gave some instructions, said, well, look at its slope. Well, look at that slope. You're going to go up $4.30 and over 1. Pretty hard to step that out when you don't have those kind of markings on your graph. So we had to find a nice whole number in a kind of a clean, clever way. So 10 comma 43. So 10 comma 43, 43, 43. Oh man, my eyes. 10 comma 43. Can I do it? 41, 42, 43. So it's going to be along this guy. Where's 10? Oh my gosh. Okay, I should be able to see that it's just 2 over, so it's like right there. So that's 10 comma 43, which gives me a nice clean integer to graph with. And oh geez, can I go that far? Come on, pinch, pull, whatever you got to do to make this thing smaller. Here we go. So I'm going to try to go through this point. See if it'll snap into place. So there's my graph, and like I said, that works beautifully in MyMathLab as long as you feed it some nice points. Okay. Moving on. Now we've got, fill in the blank, we've got a nice little statement. It says the statement F varies inversely. What? That is not the same catchphrase as we had before. F varies inversely with D. Well, okay, this is something different. Here it is right here. It says, if X and Y represent two quantities, then the catchphrase Y varies inversely with X, or Y is inversely proportional to X, right? So that's what we're looking for now. That phrase or this phrase. And when you see those phrases, it's an inverse variation problem, which means Y equals K over X. Now, if we go back to the direct variation problem, you can see direct variation problems are linear. You can see that they're linear here. And they go through 0, 0, okay? And so they're going to have a slope and all that. Oh, another thing to realize with direct variation problems, and I have seen other direct variation problems where they're, anyways, it's a combination of them, so we'll leave it at that. But one thing that you see here is as X increases, y increases. And that's kind of a characteristic of a direct variation problem. As x increases, y increases. As you go to the right, you also go up. That's not the case for an inverse variation problem. For an inverse variation problem, as you can see with the little graphic I put in here, as x increases, what did y do? Y decreases, right? If we start there like at 1, we're way up here. But then as x gets bigger, like let's say out in 10, look at y got really small, maybe down to 1. I'm just kind of guessing the points. But so inverse variation, as x increases, y decreases and goes down. Okay, so that's a telltale sign of inverse variation, and we still have a k, which is also the constant of variation like we had on the last problem, the direct variation problems. Let's see if we can do this. So the very first thing we see, it says number 7, suppose that y varies inversely. Up there it is, y varies inversely. Y is inversely proportional to x, rather. So right when we see that, we know for sure we are going to write down y equals k over x. Then it says when x equals 8, y equals 5. Well, that's just a point, right? 8, 5. Now complete A through C. First thing they want is k. Well, that's going to be easy because all we need to do is replace the y value with 5 and the x value with 8. No problem. Y value with 5, x value with 8. Solve for k. Well, if I'm going to solve for k, all I have to do is multiply both sides by that denominator, which is 8. So I multiply both sides by 8, and 8 reduces, leave me with k equals 8 times 5 is 40. So k is 40. Okay, so now go back to the formula, and I guess I'm using this color now. We said k is 40, so we replace k with 40, and we've got our equation. What is our equation? Our equation is y equals 40 over x. Got it. Y equals 40 over x. And then what else do they want? They want us to, okay, so we've got our equation now. I'm going to write down. We've got our equation that defines this situation that they gave us. Y equals 40 over x. It's an inverse variation problem with a k value of 40. And they're saying, oh, by the way, what happens if I give you, whoops, that's an x value, so I'll make it blue. What happens if I give you an x value that's 16? No problem, I got a formula for that. I just take y equals 40 divided by 16. Now be careful, because sometimes my math lab does get a bit picky. Type in the integer or simplified fraction. Okay, no more decimals on this one. We got to simplify the fraction. And so, yeah, you could simplify that. And, your brain is going to do it. Some people are fast, some people are slow. But you're looking for the biggest common factor, and you might say, oh, I think I see an 8. So you're thinking, okay, there's a common 8. I probably don't need to show you this, right? 8 times 5 is 40, and 8 times 2 is 16. So those common 8s, oh, there we go. We just reduced the fraction to 5 halves. So we just got an answer of 5 halves. Why? So when x is 16, y equals 5 halves, and they asked us to please use a simplified fraction. Otherwise, they're going to hit you with a negative response, like you suck. No, I don't think it says that, but it says something, right? And it says try again, big red bonk. We always like to see the green fabulous or excellent or I love you or whatever it says. Number 8 says, what am I? Is that the last one? 7, 8. We have one more after that. The rate of vibration in oscillations per second, V, of a string under constant tension varies inversely. First of all, you want to make sure that you know that it says V, the vibration of a string V varies inversely with the length of the string. Okay, and so you can stringed instruments would show this, right? The length of the string, the vibration or oscillation per second changes depending on the length of the string. This also is true with trumpets and trombones, and they got these long, the longer you got that, the length of the tube and all that stuff has different oscillations, and different oscillations makes different pitches, kind of cool. And then of course you've got your lips that can make it. Okay, I'm not a trumpet player. I don't even know why I'm talking about that. So it says the rate of vibration. So it says it varies inversely. So we know it's an inverse variation problem. Let's use the variables here to match up with this situation, okay? So the variables here would be V. I think I would write it like this. I would say, so it says V of a string under constant. So it's going to be V equals K over L. So it has the same look. I'm just using the variables. And the reason why you want to use the variables they're using is because what I like to do with word problems, because these problems are not that hard, but in the word problems is like, where do things go? Well, first of all, I like to do this. Well, let's see. Our ordered pair, for thinking about this like graphing, it would be L comma V, right? And what is L? L is, they told us, L, let's see, varies with the L, the length. So the rate of vibration in oscillations per second of V of a string under a constant tension varies inversely with the length. So L is the length of the string. Okay, what's V? V is the oscillations or vibrations, which is just oscillations per second. So that just kind of helps us figure out where to put things by doing that. Part A, right here. Part A says if a string is, and I'll use some color. I don't know what color I want to use. I'm changing colors up on this one. It says if a string is 34 inches long, well that's going to be L, right? So I'm going to go ahead and write that in, 34 inches long. And vibrates, well, we'll make the vibration yellow, I guess. And vibrates 810 times per second. Find the function that relates the vibration to the length of the string. Oh, so we need to come up with this function, right? We need to come up with this function. And so what do we have? Well, we have a lot. We have vibrations, right? And we have string length. Good. We got a lot. So let me see. What were the vibrations? 810 vibrations per second. The K value is what we don't have, but that's only one. Oh, let's see. We have string length with 34. K value is the only thing I don't have. That's one variable, and I can solve easily by multiplying both sides by 34. And that's going to reduce. And I got K equals what's 34 times 810, a big number, 27,540. And that's the K value. Well, if you know the K value, remember that K value is going to go into the original formula, and we will have actually a function or a formula, inverse variation problem. V equals the K value, which was 27,540 over, and what was the variable? L, the length of the string. So the vibration, which is oscillations per second, equals 27,540 divided by L, the length of the string. Hey, we came up with this cool formula when we want to construct and build our electric guitar and start a rock band. The rate of vibration of a string that is 54 inches long is, so on part B, I guess I'm going to put part B right here, go to my trusty formula here. V equals 27,540 over L. And on this occasion, they're telling us, we gotta get the right color, the rate of vibration of a string that is 50, oh, they're telling us I got the wrong color. They're telling us the length of the string, 54 inches long. That's that part. That's that part. They're giving us 54-inch long string and they want us to question mark, figure out what the vibration is. So no problem. We got the formula that'll do it. V equals 27,540 divided by 54, the length of the string. Goes right there. Well, do your little division problem. You got a calculator. You don't have to do that by hand, right? And we get 27,540 divided by 54 is 510. Oh, now it doesn't want to work. There we go, 510. And this is vibration. And if you go back to the original problem, it said these are oscillations per second. So this is, so when the string is 54 inches long, the oscillations per second is 540, or 510 rather, 510 oscillations per second. And I think that is the last problem. Is it? Oh no, I just fooled you. Fooled myself, really. Now I'm depressed. Let's see, number 9. Number 9 is switching it up just a little, just a tiny bit, and they're using the word jointly. And no, it's not what you think. It's not that. It's basically a direct variation problem, but adding another variable in there. And so suppose that y varies jointly with x and z. The equation you're going to use for this guy is going to be y equals k times x times z. So it is very similar to that direct variation problem, but we have an extra variable, so it's not a linear line anymore. It's actually a plane. It's 3 dimensions. I'm not going to ask you to graph that, but I think you can still figure this out. Find the constant of proportionality, no problem, because look what they give us. Come on, pen, work. They give us y, x, and z. So I'll just go crazy with my colors on this one, right? Okay, I've got a z that has to go there, and I've got a green 9 x that's got to go there, and I also have a purple 18 which has to go there, y. So you just make those substitutions. 18 equals k times x, which is 9, times z, which is 6. And you multiply 9 times 6. So this is just k times 54. You got 18 on the left side. Of course, we're solving for k, so divide by 54. And we end up getting k equals. Now, what they want this thing as a fraction or simplify your answer. Okay, sounds like a fraction to me. So simplify your answer, and the fastest way is realizing 18 is the common factor, but I think most people are probably going to do it this way. Most people are probably going to say, I see a common 9, and so they'd say 9 times 2 is 18, and 9 times 6 is 54, so they would reduce by a common 9, but then you'd also have to realize that, wait a minute, 6 and 2, well 6 times 1 is 2, and 2 times 3 is 6, reduce the common 2's, and it reduces completely to a third. So the k value is 1/3. Yay, well, write your function, okay. Remember, this is a joint variation problem, so there is your model. Y equals k, which is 1/3, times x times z. There's your equation. Now, let's go in for the final here, and that would be, what is y when, I don't remember what colors I used, x was green, when x is green, wait, what's the formula? Y equals 1/3 times x times z. And z, we used y, I can see over there, so I'll just stay consistent, and that goes there. Okay, so y equals 1/3 times 6 times 9. So essentially what you can do is just say 6 times 9 is 50. So this is what, 54? And you're multiplying that by a third. By the way, I don't know if you knew for sure, multiplying by a third is the same. It's the same as dividing by 3, if you want to know. And so that gives you 18. So we get y equals 18. And now we can say we have completed all the tasks that were in front of us. Yes, got it all done. Okay, I hope that helped out. That is the last section for this section before the test. Hope that helped out, and take care and have a great one. Study hard. Bye.